Hi everyone, thank you so much for joining us today. My name is Anya and I'm part of business development team here at Kmine. As usual, I want to remind you to please follow our LinkedIn page. That's where we post all our latest updates, events, and announcements about our future webinars and training sessions. So today we're focusing on how underground optimization principles like geometric foundation and algorithmic methods to underground design, integration, and production planning links all come together in real case studies to highlight common mistakes and best practices. Before we get started, let me quickly introduce Kmine. We began in 1994 in Ukraine, and over the years we expanded our footprint throughout Europe, United States, and Canada. And our team is a mix of software developers, geologists, mining engineers, including specialists certified under NI 43101 and JORC compliant standards. We work with a wide range of clients from early exploration groups and major mining companies as well, and we focus on delivering reliable, cost-effective solutions that tailor to each project needs. So let me give you a quick overview of what we do at Kmine. We build software solutions designed specifically for mining industry, covering the full workflow from early exploration all the way through production. And our platform includes flexible modules, both for open pit and for underground operations. And one of our biggest advantages is adaptability. You can start just with one module and roll out the entire suite later on, depending on what your project requires. Our tools help you manage geological data efficiently. You can create optimized mine plans for both short and long-term planning. And if you choose to integrate IoT or dispatch systems with our solutions, you can also get real-time monitoring to keep operations running smoothly and well coordinated. But our software is also built on real industry experience and shaped by challenges that we encountered through our consultancy work. And as I mentioned earlier, our team includes qualified persons who prepare technical reports compliant with NI 43101, SK 1300, and JORC standards that are tailored to project stages like mineral resource estimation, pre-feasibility, feasibility study, and others. And we have deep expertise across a wide range of hard commodities with a strong focus on critical minerals. So if you'd like to explore how we can support your project, feel free to leave a comment or reach out to us throughout the contact form on our website. So let's see what we're going to cover today. Today, we're focusing on how optimization principles support efficient, practical, and well-integrated underground mine planning. We'll start by looking at geometry as the foundation for optimization, then move into the algorithms and methods that power modern optimization workflows. From there, we'll see how these tools tie directly into underground design and how to connect optimization results with real production planning so the outputs are truly usable. And to wrap things up, we'll go through a few case studies that highlight common mistakes and best practices, giving you a clear sense of what to watch out for and how to apply these concepts effectively in real projects. So in underground optimization, the debate usually centers on economics and algorithms, but the real turning point happens much earlier when we decide what geometry we are even willing to mine. If we don't define a strict geometric model of the ore body and align it with a mining method at this stage, then all of the elegant IP, MIP, or MILP formulations that come later will end up optimizing something that could never actually be mined at the face. That's why the first layer of optimization is geometric, and it has to be not just descriptive, but fully computable. So everything starts with formalizing the ore body. For vein deposits, we're actually working with a body that's elongated in plan and down deep with variable thickness and occasional splays. Stratiform deposits, on the other hand, form layered volumes with a fairly consistent thickness and well-defined roof and floor contacts. Massive or stockwork systems behave differently. They compact but irregular 3D volumes with the internal lenses where the boundary of the viable zone rarely aligns with any simple plane. So each of these ore bodies reacts differently to discretization. A vein needs sub-blocking orientation-aware clustering so that the clusters follow the vein without cutting into the hanging wall or footwall. A stratiform body can work well with a straightforward 10 by 10 or 15 by 15 mining grid, making it easy to map optimal cells directly to room layout. A massive body, however, requires a spatial accessibility mask because even if the volume is technically mineable, not all parts are actually reachable from the existing network of workings. So once the ore body is formalized and discretized appropriately for its type, the next step is to link the geometry to stability. Traditionally, this relies on the modified stability number and hydraulic radius, like the Matthews Potwin framework, but instead of applying it manually during design, we incorporate it directly into the optimization workflow. Every candidate stope generated from the block model is automatically evaluated in stability space, and if it falls into the supported or unstable zones, its dimensions are adjusted until it fits within the acceptable region, or a backfill requirement is added as needed. So this matters precisely at the geometric level. We don't first build an economically ideal shape and then throw out the fracture zones. Instead, we tell the optimizer straight away that in this direction, the allowable span is no more than, say, 12 meters, and down deep no more than sublevel height. Then the subsequent optimization methods operate on physically possible objects. In most of academic work, including surveys on joint stope layout and scheduling optimization, this is exactly what's missing. Geotechnics is applied afterward, and half of the stopes in the optimal solution can no longer be constructed in the rock mass. Once geometry and stability are connected, we can add multi-criteria considerations. Even at the purely geometric level, we already have several conflicting objectives: minimize dilution, maximize recovery, maintain the recommended span for the selected mining method, and preserve a workable stope orientation. This is a typical case for MCDM methods, where you can build an AHP criterion hierarchy where compatibility with the mining methods and stability sit at the top level, recovery and dilution at the second, and the ease of routing accesses at the third. The geometric candidate is then evaluated not by a single metric, but by a weighted sum. For stratiform deposits, the weighting can lean more towards grid conformity and maintaining load-bearing pillars. For veins, it shifts toward controlling mining width and keeping the side walls stable. And for massive bodies, it focuses more on recoverability and potential scale-up to larger stopes. So if you want a more objective approach, you can use stopsys, which is you normalize the criteria, define the ideal stope as one that doesn't dilute, remains stable, and aligns with the chosen mining method, and then rank all candidate stopes by their distance from that ideal. The key idea is that this step comes before the economics. We first select shapes that make geometric and technological sense, and only after that we evaluate the financials. So now, when we talk about how geometry connects to the mining method, the link is very direct. A narrow step vein almost always pushes you towards mechanized cut and fill or narrow long hole stoping where angle tolerances are tight, and the optimization must produce stopes that follow the vein without violating minimum mining widths. A gently dipping stratiform deposit naturally leads to Roman pillar and its variations, so you start with a grid of rooms and only afterward decide which cells are profitable for the first phase. A massive ore body with typical rock strength usually points to sublevel stoping or similar methods where large stopes are acceptable and the optimizer can smooth the outline to reduce the number of separate extractions. And again, this all comes back to geometry. If we don't look in the ore body type and the allowed orientations at the geometric stage, we'll end up optimizing shapes that the designer will later have to slice apart anyway to make them fit the chosen mining method. Another important constraint at this stage is accessibility and routability. In underground mining, there is no point optimizing stopes in areas that can't actually be reached with an acceptable gradient, turning radius, and ventilation pathway. That's why we typically add an access graph to the geometric model representing levels, blind drifts, raises, and ventilation crosscuts. With that in place, we can introduce a direct constraint like reachable stope, which is true in the optimization, ensuring that all subsequent IP/MIP models consider only those geometries that are truly accessible from the existing infrastructure. In the simplest implementation, this is just a binary reachability matrix between graph nodes and stope centers. And in more advanced setups, it becomes a development cost function for providing access, which can then fit directly into economic evaluation. And it's only after all this, after aligning clusters with ore body, applying geometrical trimming, running the MCDM ranking, and confirming that each stope is actually reachable, that it makes sense to move on to the economic calculations in any linear or integer optimization models. By that stage, we are no longer dealing with idealized polygons from the block model. We're working with stopes that can truly be blasted, ventilated, and backfilled. This is exactly why geometry comes first. It defines a realistic search space for everything that follows and filters out the solutions that might look great mathematically, but will never survive in a real mine. So with that foundation in place, we can now look at how optimization actually implemented in K-Mine. Our approach starts with a simple idea. In underground mining, the key unit isn't a single block or even a group of blocks, but a stope. A stope already carries orientation, workable dimensions, economic meaning, and alignment with the chosen mining method. So instead of beginning with whichever algorithm happens to run fastest, we start with forming mining clusters that can genuinely be extracted under the site's geological and technical conditions. So the first step is building a geometric framework for the future stope. The block model is grouped into clusters according to the ore body strikes and dip, and only within the angular limits allowed by the mining method. This matters because underground methods are highly orientation sensitive. For example, when optimizing a vein deposit for mechanized cut and fill, we aim for narrow vein parallel stopes with minimal deviation. Otherwise, both planned and unplanned dilution increase. For sublevel stoping in a massive body, the stope can be larger and the tolerances on orientation are wider. And at the same time, the minimum and maximum cluster sizes are set. Small for veins, narrow veins to capture local swelling, fixed to room dimensions for stratiform bodies, so room and pillar integration requires no change in discretization. So once the spatial structure is defined, optimization can then begin. In K-Mine, the objective can be based either on quality or grade or on economics. A grade-driven mode works well for highly variable vein deposits where secure metal content is the priority. The economic mode is often preferred for more homogeneous massive bodies. For example, clusters are evaluated against cutoff, prices, and cost, and only those that provide a positive economic contribution remain in the stope. This avoids carrying marginal volumes that would later need to be trimmed manually. After choosing the objective, constraints are applied to the clusters in sequence. This is the heart of the process. So we start with geometric constraints. The stope must fit in the allowed height range, stay within the maximum width, and avoid shapes that create impractical tapers or bottlenecks. For gently dipping stratiform deposit laid out as room and pillar, spacing, room width, and height are dictated by the method, so the optimizer constructs stopes that follow those exact dimensions. For a stock work body under sublevel stoping with backfill, constraints reflect the allowable level height and room length, so the resulting stope is ready for design without later reshaping. So next come geotechnical constraints. Removing weak zones, limiting spans, enforcing sidewall stability, and if there is a section along deep with unfavorable fracturing, that section is simply marked as inadmissible and excluded even if grade is excellent. So this is crucial in faulted underground gold mines where rock quality can change dramatically within a few meters. Economic constraints are applied only after a cluster passes both geometric and geotechnical checks. Here, the system evaluates whether adding or removing a cluster helps or harms the economics, and in veins, this often focuses on dilution control. If an adjacent block brings too little metal but adds too much waste, it's left out. In massive bodies, slight reduction in average grade may be acceptable if they allow for cleaner, more productive mining shape. In all cases, the decision follows the configured rules that combine geometry, method, and economics. Refining the stope comes next. K-Mine can adjust sidewalls, modify the stope's incidence relative to the ore body, and tighten adherence to the valuable zone. The method context matters. So for narrow gold veins, adjustments keep mining with minimal and avoid pulling barren rock. For sublevel stoping in massive bodies, a refinement smooths edges and remove block model artifacts, leading to more stable drilling and blasting and backfilling. The output is set of stopes already shaped for immediate use in design. Another key feature is the ability to restrict optimization domain. Not every geometrical stope is practical at a given stage of development. Some areas may be inaccessible from current levels, located within the influence zone of active stopes, or positioned under protective pillars. In K-Mine, the engineer defines the working volume, the portion of the model where extraction is currently allowed. If optimizing a room and pillar section between two ventilation drifts, there is no point in generating stopes outside of this window. Similarly, for sublevel stoping above the haulage level, the system can be instructed not to form stopes below a given elevation. So this keeps results aligned with the real mine constraints. Throughout the process, the optimizer remains aware of the intended mining method. When tuned for narrow vein mining, it uses small cluster and tight angular limits and stricter dilution control. For stratiform bodies and Roman pillar layouts, it aligns stopes with grid-based mine discretization and preserves support pillars. For sublevel stoping in massive ore bodies, it emphasizes permissible heights and refined shapes to reduce backfill volume and simplify drilling and blasting. And all of this is handled during optimization, not after. So the stopes that move forward are workable, economically justified, and correctly oriented with respect to the ore body. K-Mine's stope optimizer does most of the hard work up front, so it starts directly from the block model, grouping blocks into clusters that follow the ore body strikes and dip, keeping each cluster within the angle limits allowed by the mining method, evaluating economics, and most importantly, preserving the geometry required by the chosen method. So by the time the engineer receives the output, the stopes are no longer abstract outlines. They already have dimension, control, dilution, heights that make sense for the method, and an orientation consistent with the ore body. So because of that, integrating them into design isn't about fixing or shaping them. It's about placing these already valid stopes into the actual underground environment of a specific mine. So the first step after receiving the optimized stopes is checking them against site-specific rules. The optimizer worked within the boundaries and constraints you provided, but every mine has local restrictions that rarely make it into public documentation, like protective pillars, areas with reduced rock mass quality, levels where drilling from one direction is impractical, or panels that must use backfill. That's why each stope gets a local status, accepted as is, accepted with backfill, accepted only with a reduced height, or flagged to be rerun under stricter constraints. So the logic is simple. The optimizer enforces general mining method constraints, and this pass enforces local mine constraints. This matters especially in narrow vein operations where the optimizer follows the vein closely, but the geotechnical requirements of a particular level may demand support or backfill for certain spans. Without this step, the designer will end up correcting the same issues later, only at a more advanced stage. So once a stope passes local validation, it has to be placed into the existing mine layout. The optimizer works in the coordinate system of the deposit, but the designer works in the coordinate system of the mine. So levels, ramps, crosscuts, and ventilation drifts. This translation is the essence of integration. In the vein deposits, mined by long hole or mechanized cut and fill, this usually means generating short axis drifts and drilling bays at the correct level, at the correct elevation and azimuth, while keeping the distance to the face minimal to preserve selectivity. In sturdy form or gently dipping room and pillar layouts, integration is mostly alignment, snapping the optimized stope to the mine's existing grid, keeping pillars intact, and using established ventilation branches. In large sub-level stoping systems within massive ore bodies, the stope shape itself is usually already sound, but it still needs a ramp or sub-level access, drill drifts, and often ventilation connection. In every case, design does not invent geometry. It materializes the geometry created by the optimizer. Once a stope is specially placed, the time dimension must be added. Optimization tells us what is worth mining. Design and scheduling determine when and in what order it can be mined. So that order varies strongly by deposit type. In narrow veins with backfill, adjacent stopes rarely run in parallel due to sequencing, ventilation, and stability requirements. In Roman pillar operations, more parallelism is possible, but only if pillar spacing and airflow aren't compromised. In sublevel stoping, level by level directionality and slot sequencing dominate. Mining a lower stope before its upstream partner may look profitable in isolation, but breaks access and disrupts production flow. So during integration, we attach precedence, links, and mutual exclusion rules to each stopes. One may be mined only after backfilling the neighbor has occurred. Another may not run in a parallel with the stope sharing the same ventilation branch, and the third may require after ramp development to level 860. So when these relationships are embedded in this stage, the scheduling system receives a coherent network of tasks, not just a list of profitable ships. So modern K-mine workflows also need to handle re-optimization. Prices change, cutoffs shifts, and new drilling updates the block model. The whole point of having an optimizer is that we can rerun it, but rerunning it is meaningless if every new stope forces the designer to redraw accesses or the scheduler need to rebuild the plan. So that's why integration must preserve the identity of the stope objects and their connections. Each stope needs a stable identifier, and each piece of development created to that stope must know it belongs to it. So this allows control updates. If the stope changes slightly, regenerate only the attached crosscut. If it changes significantly, then flag it for redesign. If only its economic parameters change, then pass those to scheduling and keep the geometry intact. The tolerance for automatic updates depends on the method. Vein mining has almost no tolerance. Even small width changes affect support and backfill strategies, so updates are usually manual. Stratiform deposits using regular rooms are more forgiving. Status updates flow naturally through the layout. Sublevel stoping is also the most flexible. As long as level spacing and height remain valid, access development can be rebuilt automatically. So by this point, the differences between deposit types become clearer. In vein deposits, optimized stopes are already narrow and aligned, so integration focuses on minimum width, local stability, backfill cycles, and generating numerous short accesses. In layer deposits, integration is about reconciling the optimizer's cluster grid with the mine's room and pillar grid without compromising pillars or insulation patterns. In massive ore bodies, integration is heavier on infrastructure, assigning the stope to the right level sequence, tying it into ventilation and power, and ensuring it can be drilled from existing sublevels. But the upside is far greater tolerance for automated updates when reoptimization occurs. So transition from optimization to planning isn't just the next step to the workflow. It's the point where the digital model of optimized stopes and geometric decisions begins to operate within the reality of an actual mine. So this is where shapes defined by optimization meet the constraint of access, equipment, operating cycles, ventilation, and day-to-day economics. Optimization tells us which stopes are technically and economically viable. Planning turns those stopes, though, into a coordinated sequence of actions that are feasible in time, space, and resources. At this stage, logistics become just as important as economics. How each stope can be accessed, when it can be mined, and what is required to physically bring it into production. Modern underground planning methods assume tight connection with the results of stope optimization, and each optimized stope is not merely a geometric object, it represents a work unit with geotechnical conditions, expected economic return, drill and blast parameters, and requirement for backfill and access. In planning, that stope becomes a node in a network where technological steps, geomechanical constraints, and time dependencies intersect. In this way, the planning system becomes the bridge between the mathematical optimality and real-world engineering feasibility. In cut and fill mining, an optimized stope isn't just a geometric shell. It represents a full cycle of repeating stages, drilling fan patterns for each slice, blasting, marking, and drawing, cleaning, placing backfill, waiting for it to cure to the required strength, and then shifting equipment to the next slice horizon. Planning begins by mapping these stages into a calendar for each stope, with durations derived not only from generic averages, but from the geometry produced by the optimizer. The longer the stope stretches along the vein and the narrower the working width, the denser the drill pattern becomes and the longer the associated draw cycle. Each stope is assigned to its own set of technological windows in the dependency graph. A neighboring stope in the same ventilation wing cannot be opened at the same time, and drilling the next slice cannot begin until the backfill in the slice below has fully cured. On the resource side, it's helpful to maintain loading charts for drill rigs and backfill plans so that peaks in cement and or aggregate demand don't overlap across multiple stopes. Economic attributes from the optimizer are used to prioritize within the accessible set. When logistical costs are equal, stopes with higher margins or better contribution to plant feed quality are mined first. Feedback loops are tracked as well. Real-paced cure times are monitored and used to fine-tune planning parameters for upcoming stopes of similar geometry. For cut and fill, the end result is a structural staircase of time shift cycles where the optimized stope geometry drives cycle durations, and geotechnical and ventilation rules determine the mining sequence. This approach minimizes delays caused by backfill, maintains selectivity, and helps keep plant feed quality within the required range for each period. In room and pillar mining, the optimized stopes are essentially the economically preferred cells within the regular grid. But the actual mining sequence is driven less by economics and more by roof stability and the preservation of load-bearing pillars. Planning starts with laying out panels and access headings. Primary development is arranged with ventilation and haulage in mind so that the airflow conflicts and unnecessary machine maneuvering are minimized. From there, dependency network is built across the grid. Two adjacent rooms cannot be taken without a pillar between them. A cell cannot be mined if doing so breaks the ventilation circuit. And the rooms connected to the same narrow drifts cannot be worked at the same time. Scheduling operates on this dependency graph, assigning time windows to optimize stopes panel by panel. Within the set of geomechanically permissible options, economic indicators help determine priority. Cells that improve metal output in a given period or help close a tonnage gap move forward first. Backfill strategy is also an important nuance. If the optimizer marked a cell as requiring unloading of adjacent pillars, the plan inserts a partial or full backfill or postpones extractions of neighboring cells until the fill reaches design strength. For larger panels, it often helps to introduce a block panel rhythm. The panel is divided into sub-panels, each treated as a small self-contained project with its own logistics, and which reduces equipment that hiding and keeps production more consistent. Throughout the process, roof sag and pillar conditions are monitored as operating data comes in. The dependency graphs is updated, and the queue of optimized stopes is resorted to maintain production pace without compromising stability. In sublevel stoping, the optimized stopes already align with the sublevel layout, height, orientation, required backfill type, and expected drilling and draw volumes are all predefined. Planning then focuses on synchronizing 3 parallel streams across multiple levels: drilling, blasting, and backfilling. The first step is grouping stopes into panels by level to keep work concentrated and reduce machine travel distances. Each panel is then given a cycle. Drill the first stope, blast and draw it, drill the second in parallel, backfill the first while blasting the second, and so on. So a checkerboard sequence that minimizes idle time. A dependency graph enforces operational restrictions. No blasting next to a stope where paced backfill has occurred. No drilling in areas with elevated post-blast gas, and no simultaneous drawdowns if they compete for the same conveyor or loading drift. Economic attributes guide prioritization within each panel. When drilling capacity is tight, stopes with higher margins per drill meter move first, and when paste supply is the bottleneck, the preference goes to the stopes requiring smaller backfill volumes per cycle. Access logistics are integrated directly into the schedule. If reaching a stope requires a long blind drift, its start is delayed until development is complete, while closer stopes are advanced to avoid production gaps. To maintain vertical stability, a level panel strategy is used. Mining progresses from bottom to top within a panel with control windows for ventilation, personal movement, and equipment clearance. Regular re-optimization ties everything together. Actual drilling performance updates, cycle durations, and fine-tunes the checkerboard rhythm without forcing a full rebuild of the schedule. In sublevel caving, the optimized stopes are interpreted as geometrically and economically acceptable zones along the future caving front. But the actual planning unit isn't a single room or isolated stope. It's a continuous cave front of an entire panel. The core goal is to maintain uniform cave propagation and stable draw control so losses stay low and waste inflow is minimized. Planning starts by building a panel map, rows of draw points, the sublevel sequence, and the target advance rate of the front along strike. The optimized zones are connected to these rows as priority draws area. However, only those zones that located on the active front, which are guaranteed draw conditions, and ventilation, only those are scheduled. The dependency network imposes strict limits on advance. The front cannot move too far ahead along strike while leaving undrawn rows behind, or the front becomes uneven and recovery drops. Three-dimensional safety windows informed by subsidence and microseismic monitoring add another layer of control. If monitoring data shows accelerating deformation in section, the plan reduces draw there and shifts activity to more stable areas, even if the optimized economics pointed towards a different order. Economic weighting is applied only when choosing between two equally ready rows. Those with a higher expected grade and better selectivity, which is based on the Maxim model, are mined first. On the calendar side, loading charts are run both by sublevel and by draw point rows to avoid bottlenecks at transfer points. The system remains adaptive through periodic reevaluation and of optimized zones using actual grades from draw control. If excessive dilution appears in an area, the draw sequence is adjusted and some optimized but riskier zones are deferred until the front stabilizes. So when optimization is viewed purely as an algorithmic exercise, the workflow looks deceptively simple. You just have a block model, you have economic inputs, and you have a model that generates stopes for a chosen mining period method. But once this process is applied to real data with an actual deposit, the problems begin to appear, problems that rarely show up in textbook examples. Vein thickness may fluctuate unpredictably, contacts may be irregular, sampling gaps can distort local grades, geotechnical limits may conflict with the selected stope height, and most problematic of all, you may end up with shapes that look profitable on paper but are not truly mineable underground. That's why it's helpful to look at a few common situations where technically correct optimization still produces designs that are awkward from an engineer standpoint, and to show that what can be done differently to avoid these pitfalls. So the first scenario is typical for narrow veins with variable thickness. The root cause is almost always the same. The original block model was built on a grid convenient for the geologist, not for the mining designer. The block is too large relative to the average vein thickness, and as a result, even an optimizer that handles clustering and angular ranges is forced to include waste to assemble a continuous stope at all. In the model that looks acceptable, plant dilution occurs, and the economic indicator is positive, but when the result moves into design, turns out that the actual mining width exceeds the allowable limit for the stope or for the mechanized cut and fill fleet by 0.7 or 1 meter. The designer naturally trims the outline back to the permitted width, and the original stope economics collapse with it. So this can be perceived as an optimization error, but the real mistake lies in model scale. The best practical approach for such ore bodies during data preparation is to switch to a finer discretization in the vein zone, use subblocking at contacts, or define the vein as a separate domain with its own grid, so the optimizer does not have to widen it by pulling in barren rock. So then both shape and economics will be closer to what can actually be mined. The second common scenario appears in stratiform, gently dipping, or otherwise well-organized deposits where the mine relies on a regular grip development pattern. In this case, the mistakes usually goes in the opposite direction. The optimization is run on standard cubic block grid without considering the mine's actual discretization. The result is an irregular stope outline that in some areas pushes into future rooms, in others cuts across plant pillars, and elsewhere carves out thin slivers that have no practical place underground. From the optimizer point of view, everything looks fine, right? So it's simply a collection of blocks with positive net value. But from the design standpoint, it's chaos. Trying to fix this after the fact does not work. The moment the engineer snaps the outline back to the mine's room and pillar spacing, much of the model economic benefit disappears. The proper workflow for these deposits is different. The first lock in the mine grid, the discretization used by the project, whether it's 15 by 15 by 3 or 20 by 20 by 4 or another scheme, and then evaluate cell economics using the same discretization. When optimization operates on the same cells that appear in the design model, integration becomes seamless instead of a geometric correction exercise. Well-structured K-mine workflows follows exactly this approach. Optimization runs on clusters aligned with the mine's grid steps rather than on isolated blocks, ensuring the outputs are immediately compatible with the real underground layouts. And finally, the third scenario appears in massive and stockwork deposits. At first glance, this seems straightforward. The ore body is large, the grade variability is moderate, big stopes are permitted, access development is relatively flexible. But yet, this is exactly where errors often emerge at the boundary between technical limits and economic optimization. When the optimizer sees that adding a few marginal blocks slightly increase metal with only moderate dilution, it naturally expands the shell. In the block model, this looks like improvement, a cleaner, fuller shape, but in reality, the outward expansion may push stope into a zone where the ground control plan requires pillars, extra support, reduced stope height, and the designer is then forced to either trim the stope back or split it into two smaller rooms. Either option affects backfill volume, access length, and even the schedule. So to avoid this, the optimizer needs to interact more strictly with geotechnical constraints at stope boundaries. If there are zones of reduced stability, they should be flagged explicitly and excluded from the economic shell rather than left for correction during the later design stage. This is a classic example of how a slightly more conservative optimization leads to a smoother, faster workflow and cleaner final project. So now let's turn to what actually helps, the best practices. First, it's essential to separate zones based on data quality. If one part of the deposit has dense drilling and another is partially sampled, there is no reason to apply the same grid resolution or constraints to both. In well-drilled areas, you can allow finer optimization and more detailed stope shapes. In poorly drilled zones, it's better to restrict the geometry upfront to stable, easily designed forms, so you don't end up chasing questionable tongues of ore with expensive development. Second, for veins and other selective mining situations, a preliminary geometric smoothing of vein contact is often worthwhile. Instead of using a boundary that jumps from 0.8 meters to 1.4 meters every few blocks, build a smooth surface that yields more regular stope dimensions. While this may trim the theoretical maximum recovery, it usually improves mining consistency and reduces dilution, both of which tend to matter more in underground operations. And third, tight coordination between optimization and scheduling really pays off. In the first scheduling pass reveals that certain stopes don't fit due to ventilation, access, or sequencing conflicts. It's better to feed those constraints back into the optimizer and rerun the model instead of manually trimming shapes afterwards. This way, both the economic and engineer outcomes emerge from a single and consistent set of constraints. So to see how this works in practice, let's consider a real mine example. After introducing full 3D optimization, the team initially generated about 15 to 20% more stopes that met their acceptance criteria compared to manual design. But once these stopes were placed into the actual mine layout, roughly a third of them conflicted with the ventilation on that level or required access drifts too long to justify the expected return. Instead of trimming these stopes later in design, the team fed two additional constraints back into the optimizer: a limit on maximum access drift length and an assignment to a specific ventilation wing. With those constraints incorporated, more than 80% of the optimized stopes entered the project without any modification, and the time needed to align them with planning was cut almost in half. So it's a great illustration of a key best practice. The goal isn't to perfect the geometry manually, but to push the real-world constraints identified during interrogation back into the optimizer so it produces shapes that already fit the mind from the start. And that's it for today. Please drop your questions below in the comment section so we can answer them there, and I'll see you next time.